previous lectures that I've given on regression show these really simple examples where everything sort of works out neatly and nicely. And those are the examples that I typically saw in the statistics classes I took when I was learning about statistics. But in general, regression is actually kind of a hard thing to do in real life, and there are lots of different ways in which it's complicated. So here's some examples of things that can mess up a regression analysis very quickly. One is confounders. We'll talk about those. Complicated interactions between variables. You saw one of those with a continuous variable. Skewness, outliers, nonlinear patterns between variables, variance changes, unit or scaling issues, overloading regression, and correlation and causation. All of these different things are different ways in which you can trip yourself up if you're doing an analysis and you're not paying careful attention. So regression analysis, while it's really powerful and it seems like it's really easy to do it well takes a lot of effort actually. So the ideal data for regression look like this. You have two variables here, parent and child, and this is the Galton data that we used in our earlier examples, and the cloud of points looks sort of like an oval. And the reason why this is the ideal thing is because this is what regression was originally designed for, was to deal with the case where the data was multivariate normal. In this case it's bivariate normal, and it's kind of got a cloud shape. All the sort of assumptions for regression work out just perfectly, but that's almost never how it looks in real life. So for example, there are confounders. So a confounder is a variable that is correlated both with the outcome variable, whatever that is, and the covariate variables. They can change the regression line and give you even opposite regression lines of what you'd expected to see if you don't account for them correctly. They can sometimes be detected by careful exploration, and in particular, data visualization and exploratory analysis are important for determining potential confounders. You saw that in the example analysis that I distributed, and you've also seen it as I've gone through some regression examples here. But here's another example from the Millennium Development Goal data. Again, we're going to be downloading data from the World Health Organization on childhood hunger. And so when I download the data set, I again get this data set where I have the country of origin, the sex, the year, the World Health Organization region, and then a numeric variable which tells me the percent hungry. And so if I plot, again, the percent hungry versus the year, you can actually see the same sort of scatter plot you saw in the previous lecture. But now you see, if I color that by the different region, you see that there's definitely a huge amount of variation by region, and that the lines would be totally different if I fit a regression line to each specific region. In particular, say Europe, for example, is always down here at the bottom in these dark blue circles, whereas these light blue circles are Southeast Asia. So region is correlated with the year. In other words, in this data set, we have more measurements that come from certain regions in certain years. And so we actually performed here a linear regression analysis where we relate the year of the measurement to what region it's coming from. And if you do an ANOVA, we actually get a significant p-value and a relatively moderate f-value. I wouldn't say that this is a super strong association, but it's clearly associated with year. Region is also correlated with hunger. That we definitely saw in the other plot. And so we can do another ANOVA, and here we get a very, very large f-value and a very tiny p-value, suggesting that there's a strong correlation between the percent who are hungry and what region of the world that they come from, which isn't really that surprising. So if we include region, we actually get quite a complicated interaction. So you can imagine where you have a linear model that relates as the outcome variable, the left-hand side of the tilde, the percent that are hungry, to the right-hand side of the tilde, the variables in the model, the year plus the region plus maybe an interaction between year and region. Well, if you include an interaction between year and region, then for every single one of the different colors, you get a totally different regression line. And so to say, for example, to plot the regression line just up here for Southeast Asia for the light blue dots, you actually have to do two coefficients have to get added together to get an intercept term, and two coefficients have to get added together to get a slope, and they have to be the right ones. So it starts to get pretty complicated to be able to identify what are the right variables to include in the model, and in particular, as you saw with the multivariate analysis, the interpretation can become quite difficult. So now I'm going to talk about a second example. So here I've got some income data. So this is income data that's available from the UCI database. And so this is actually census data where we have the age of a bunch of individuals as well as their income in a particular year. And so if we make a plot, we can actually see one of these plots where this is the income on the y-axis and the age on the x-axis. And you can see most of the points are stacked here down up against the edge, this edge of the graph. And so that's an example of what's called right skew data. So for example, if we make a histogram of just the income data now, we see that there's a lot of low incomes and then a long tail out to the right for much higher incomes. And so this long tail out to the right is a right skew. And it violates one of the assumptions of fitting a regression model and can lead to some difficulties in getting reasonable standard error estimates in particular. And so what you can do is actually often when you have sort of right skew data like this, a very common transformation is take the log of the income. And so here now we see something that looks a little bit nicer, a little bit more symmetric, although there's clearly some kind of bump out here, which is a probably an unmeasured confounder that we would have to explore to try to figure out if we were building this regression model. So then if we create another sort of smooth scatter of age versus income after we've taken the log of the income values, we get something that looks a little bit more like the regression cloud that we're looking for when we're performing these analyses. An important thing that to note is that here I've added 1 to the income values before I take the log. And the reason why in this particular case none of the income values are equal to 0, but if some of the income values were equal to 0, if you took the log it would make those values NA. And they would just get ignored by R, but they might be incredibly important if you have a bunch of 0 values that actually mean something in the analysis that you're doing. Another issue that you run into very often when you're performing an analysis with regression is outliers. So outliers are data points that do not appear to follow the pattern of the other data points. So that comes from, that quote is a quote that I kind of like, and it comes from this paper, a data set that is 44% outliers. So one way that people have defined outliers is definitely in terms of the magnitude, but just the orientation and location of the points can also give you some information. So here's an example. If you saw a distribution like this where you have almost all of the values over here down near under 200, and then you saw one value that was almost 1,000, you might think this is an outlier. And so another example that you might see is an example where it might be real. So in that previous example, it wasn't clear necessarily that the value that I was looking at was a value that was due to a real measurement or whether it was potentially due to some error in how the people have collected the data or written the data down. But in general, you might actually see outliers that are actually just real data points. So for example, if I add to that income data set the age and income of Tim Cook in 2011, I get an age of 52 and an income of $378 million. And so if I make that same scatter plot, you see everybody else's income is kind of squished down here at the bottom, and then Tim Cook's is way, way up. And so essentially what you're seeing here is that one outlier can have a dramatic impact on sort of the way you visualize data, certainly, but also on your analysis. And in this case, it's not clear that you need to remove this point because that is a real salary, that is a real person that you collected the information from. It wasn't a mistake. Finally, here's another example of an outlier that doesn't fit the trend. This is what I mean by it doesn't always have to be extreme. None of these points is extreme in either the sort of the x or the y axis. They're sort of all in the same range. But you can see that these points follow a very specific parabola, and then there's one point that doesn't land on that parabola. So this is a point that doesn't fit the trend. I would call this an outlier when I was doing my analysis, in the sense that you can imagine fitting a very, very nice curvy line through these and then having a big problem with this point right here. So an important thing to note with outliers is that you need to know if they're real or if they're not real. So if they're real, you should remove them only with very, very extreme caution, right? So that's a data point that you know is real, you know it's correct, and you're removing it, you need to have a good reason for it. However, you might have cases where outliers are due to a machine being broken or somebody recording a number wrong. In that case, it may make a lot of sense to just remove the outliers. If you don't remove outliers, or if you do, here are some other things that you can use to sort of help your regression analysis. First is a sensitivity analysis. You can toss the outliers out and keep them in and fit the model in two different ways and see if you get very big changes in the results. If you don't see any big changes in the results at all, then maybe it doesn't matter too much if you leave the data in or out. You can take logs if the data are right skewed. So we talked about that a little bit with the previous slides. And so if there are lots of outliers, that's often a transformation that you can take. Finally, there are robust methods. So we've been doing a lot of averaging of a specific kind when we're doing our regression analysis, but there are approaches that are more robust to outliers or distributions that aren't necessarily very nice and normal and symmetric. And so here I've linked to a bunch of robust methods in R that you can use, and in particular RLM is the robust version of the LM function that we've been using to fit linear models in the last few lectures. Another thing to keep in mind is that a line isn't always the best summary. So these actually all are lines that have the same correlation coefficient. If you go and check out this example at the Wikipedia page, you can see why they all have the same correlation, but they're all dramatically different results. So you might imagine here in this case, you wouldn't even think that a line would be the right thing to fit. It might be a curvy fit. Here, maybe a line is the right thing to do. Here, it's not clear. There's an outlier. You're not sure if it's real or not. In this example, you might think of this as more of a factor analysis since you only have sort of two specific x values to be considered. So in general, you might want to, it's very important to look at plots of the data that you have and make sure that there isn't something strange or nonlinear going on that doesn't fit very nicely into the regression framework. One reason you need to check for sort of nonlinearities is because you can end up saying some pretty silly stuff almost by accident. So here's an example. This is actually a paper that was published in the journal Nature, and in this paper they actually plotted the sprint times for women and for men, and then they projected out into the future and suggested there was a time when women would run sprints faster than men. And that in and of itself is not necessarily a terrible analysis, but if you sort of project these lines all the way out into the future, eventually both of these lines cross zero. And so the authors omit to mention, however, that according to their analysis, a far more interesting race would occur in this year when times of less than 0 seconds will be recorded. So using linear models when it's more likely that the times are sort of dropping off and then leveling off rather than going away to zero can make you say sort of things that would be a little bit silly. In this case, it was even spotted by a set of high school students in Texas, and they also got a paper published in Nature where they responded to this particular example of a bit of a silly linear regression. Another thing to keep in mind, in addition to nonlinearities, is potential changes in the variability. So all of these regression models assume that there's a constant variability around the line that you fit. So here actually is a set of data about liver disorders, and these are a couple of different molecules that they're looking at, and they want to be able to predict, say, AAT from GGT, in particular log GGT. And so if you make a plot of these variables, you can see it looking like the scatter plot is getting a little bit bigger out here to the right. If we fit a linear model relating the two variables and then make a plot of the residuals, so remember the residuals are what's left over after you subtract the regression line out of the points, you actually see that indeed there's sort of this funnel shape where over here on the right for larger values of GGT you get much larger residuals, so the variance is much bigger. This example actually comes from this website, which I've linked to here, but there are a couple of different things that you can do when the variance is changing. A few of the examples are using Box-Cox transforms, variance stabilizing transforms. These are both statistical procedures that you can pre-process your data with. You can use weighted least squares or standard White, Huber-White standard errors. Both of these are sort of statistical approaches that try to estimate the covariance matrix or take the covariance matrix into account. Um, and in particular, they try to sort of estimate the fact that the variance is increasing over time and include that when they're doing the modeling. Another thing to keep in mind is variation in units. This is an issue in science in general, but a major issue in statistics is that you got to keep track of the units that you're using. So, for example, here is all-cause deaths in children 1 to 59 months, and so this is all the children that died in a particular country versus their income per person. And so you can see, for example, there's a huge number of deaths up here, but those are all deaths from one country that is a very large country with a very large population. I think this is India in this case. So if you actually get data like this, it might make more sense to standardize where each country is number of deaths is divided by some denominator. So in this case, it's the number of deaths that occur per 1,000 in children. And so you can actually see that you get some of the points will sort of definitely reorient themselves, and it might make a lot more sense to deal with relative units than to deal with the absolute units. Um, when there's variation in units, you might want to standardize, like I just said. You might want to say per 1,000 or divide by some denominator. Um, it does affect model fits and interpretation and inference. So in particular, you might want to pay attention to if you change the units, how that's going to change the interpretation of the regression coefficients that you estimate. Another issue that always comes up when you're doing a large-scale epidemiological studies of using regression is that you might end up with an overloaded regression model. So in this case here, I've shown you an example from a paper. This is the link to the paper here, where they were basically looking at the causes of mortality, and they were looking at that by whether the medical industry was private or not, and then a bunch of other variables about the countries, including GDP, whether they were at war, and so forth. And you can see that there are a ton of terms in this regression model, and it makes it very difficult to interpret many of those terms. And in general, when you have this many terms in a model, it makes it very difficult to be sure that what you're estimating really makes sense in the sense that your assumptions hold. So in particular, this model was, here's a link to a blog post where this model was sort of deconstructed a little bit. And so in general, the fewer terms that you can include in the model, the better, the more interpretable that model will be. Finally, the last one that you probably already know a lot about is correlation and causation. So this is a comic from XKCD where this guy says, I used to think correlation implied causation, then I took a statistics class and now I don't. So she says, sounds like now the class helped. And he said, well, maybe, because it's not clear that the class was the causal reason for him changing his mind. So correlation and causation is a bigger issue which has to do with, can we actually discover the sources of causation? But even if you're not going to go that far, even if you're not going to try to figure out what actually caused something to happen, it can be something that you should pay attention to when you're performing regression analysis. So here's an example. In this case, they weren't actually looking for a causal effect necessarily, but they were looking for associations. And so what they did was, in this analysis, they plotted the number of Nobel laureates per 10 million people in population on the y-axis. So number of Nobel laureates on the y-axis. On the x-axis is the chocolate consumed in kilograms per year per person. And so you can see that there seems to be a trend or a relationship between these variables. So the more chocolate that you eat, the more likely you are to win a Nobel Prize, which is good for me because I like chocolate. But it seems like there might be other explanations for why this is true. And so here's an example where it got a little bit silly. In this blog post, they responded that they just calculated the number of letters that there were in the names of the countries, and they plotted the number of letters in the names of the countries versus the Nobel Prize, and they actually got a much better correlation than they even got in the original paper. So here you don't see the pretty flags, but you can see that the correlation is probably pretty good because you have this point, especially because you have this point way out here. So what this suggests is that there's probably some other mechanism going on that's driving this relationship. So when you're dealing with correlation versus causation, an important point is using caution when interpreting your regression results, and in particular paying attention to if there are surprising associations, what are the potential alternative explanations? Is there a reason why these two variables might be related that has nothing to do with the relationship between them? It could be a confounder that is sort of surprising you or making the relationship seem like something it isn't. So that was a brief overview of a bunch of different things that can go wrong with your regression analysis, and hopefully you can address them all and have great regression analyses that will be useful for you.